Hey everyone, welcome to our next video. This one is, excuse me, 2.3, which is functions and relations. So I'm going to go ahead and write that down. Functions and relations. So of course in a normal class, I really do like to kind of talk about these things, but unfortunately for y'all, I just kind of have to tell you what it is. So a relation is kind of what it sounds like. It relates one element, well, we'll say an element, in one set to an element in another set. Now the thing to know about these is that they're describing two different elements here. So often what's going to happen is we have like an x and we have a y. So you're having like multiple variables happen. With these multiple variables, we have what's called our domain, which is the set of input values for the relation that we're dealing with. Often your input values are x values, but it doesn't have to be x. But I'll say that it's usually x or t or something like that. T is often when you're doing like word problems. If it's based on time, you're going to use t. But usually we're using x's as our domain. Then we'll have our range. And our range is the set of output values for our relation. And so usually this is going to be like our y values. So let me show you an example of a relation. So an example, this one I'm writing as a set, so I'm going to write just like points. So here's my points. I have a Longhorn, comma, UT Austin. So that's 1 point. So you have to remember that these don't have to be like numbers, like they can be words. It's just relating two things together. We'll have Bulldogs and LA Tech, or La Tech, I think is how we are technically supposed to say it. Bulldogs and Georgia. So these are like mascots. We've got Tigers for LSU. And we have Tigers for Auburn. Kind of ran out of space there. Sorry about that. So it's looking like my X values are the mascot. So that's like my input. And then my Y values are the school. So that's my output. So this is just an example of some kind of relation. Now my function Oh, so let me talk about this real quick, actually. Sorry, go back. If I asked you for the domain of this, you would just write out for me all of the X values that we use. So we'd have Longhorns, Bulldogs, Tigers. This is the domain for this set. If I ask for the range for this set, it'd be all the Y values. So you'd write all the Y values for me. And you'll notice that for the X values, I didn't repeat any. Like it's not like I wrote Bulldogs twice. I didn't have to write Tigers twice. So you don't ever have to like repeat. All right, now let's talk about a function. A function is a specific type of relation. So it's a type of relation that relates one element in the first set to exactly one element in the second set. So a little bit of a point here for functions. They're specific about their x and y values. So what's happening here is the same x cannot map to different y's. That's what happens with a function. However, you could have two different x's that have the same y. So we can have two different x's with the same y. Something else about functions is all x's in the domain must map to something. So they have to map to some kind of input. You don't want to ever have, some kind of output. You don't want to have an input value that just has no output associated with it. So in a function, all the x's in the domain are used, and then also no x has two different y's. So our earlier example up here, coming back up to my mascot example, do you see how we have the same x value going to different y values? That is not allowed for a function. So that happened with bulldogs and also with tigers. So our earlier example is not a function. Now it's still a relation and we can still find the domain and the range of it, but it's not a function. However, if we flipped the x and y values, so if we made school our x and mascot our y, then it would be a function. And just to be clear, there are real life examples of functions. So, in general, you can think of something that you don't want the same thing going to two different y's. An example of a function in real life, let's think. Well, what if I did for my domain, I let it be a campus-wide ID, and then for my range, I could just say our names. So this is important because you wouldn't want to type in a campus-wide ID and come up with two different people's names, right? Like you would want one campus-wide ID to one name. However, it is possible for two people to have the same name. So it's like for our range, we can have repeated values, but for our domain, we do not want repeated values. So I hope this makes sense. So like if I flipped these, that would be a problem, right? Because if I made my name my domain, let's say I go into Workday and I'm looking for somebody and I type in their name. Well, usually that is what I have to do because I can't actually see y'all's campus-wide ID, but it would be a lot easier to find people if I could see your campus-wide ID, right? Because it would be a lot easier for me to go into Workday and type in that and I'd come up with one person. Usually what happens, I have to type in names and there's people with the same name. So I just got to go through and like find the picture that matches it. So the idea is functions are important in real life. Another example I could think of, let's say like a relationship between your driver's license and your name, right? So I don't want to have repeated driver's license numbers. So that would have to be my domain. Um, let's see another one. Like a license plate on a car, right? We can have the same type of car, so that's like the Y value, but every license plate should be unique. So that's going to be my X value. So that's the idea. We just want unique X values. That's basically the point. Now, also with functions, we have what's called a vertical line test. Sorry, I'm getting a call, but I'm doing my video, so I'm not going to answer it right now. Sorry about that. So for our vertical line test, this is a way if we want to like graphically test if something is a function. So what we pretend to do is basically hold up a vertical line and we should see at most, here, let me not write it super shorthand, at most 1x graphed at a time. It's a little hard to explain with just words, but I'll show you in an example. So example 1, we'll say function or not. And so for A, let me make up a few. So this one I'm going to make like a list of points. Okay, B we'll do 1, -1, comma 1, 2, comma 2, 1. And then I also made some that have um, graphs. So let's do these. Mm, draw that one like that. Okay, so let's start with A. So what we're looking for whenever we're doing a function, now this one didn't give us a domain and range, so we don't really get to check if like all the elements in the domain are being used, but we'll just look for any repeated x value. Since all my x's are different from each other, this is a function. Now you'll notice that we do have some repeated y's, but that's okay. That's not a problem. We only need to worry about repeated x's. Part B, I notice that I have a repeated x and it's going to two different y's, and that is not allowed. So we would say, no, this is not a function. It's just a relation. So we have the same x going to different y's. So that is why this one is not allowed. Now let's say that I had just repeated the point, like I just wrote the point twice, like 1, -1, and then I wrote 1, -1. That would be okay, even though it's repeating. If it's going to the same y value, it's all right. The problem is that it's going to different y values. Now part C, we're looking at our vertical line test for the graphs. So imagine you held a vertical line up to this graph. Do you hit more than one x value at the same time? Meaning, does our x have two different y's? And we'd say, yes, it does. I have a y at the bottom and I have a y at the top. So this is not a function. What about for D? If I imagine a vertical line going anywhere on this graph, am I ever hitting, like at any x value, am I hitting 2 points at a time? No, I'm not. So this is yes. This is a function. It passes the vertical line test. And then lastly for E, imagine a vertical line. Okay, so this one's kind of interesting because through these little dots here, I am technically hitting two different y's, so it looks. But be careful, this one right here is an open circle, so it's not actually defined there. It's only defined here. So this would be, yes, a function. And we'll also come back to talking about some more domain and range. But for now, we're going to move on to um, talking a little bit about function notation. So function notation looks like this. If I say f is a function of x, the way that I can write that is like this, f parentheses x. This means f is a function of x. So this is saying that x is my domain. X is my input value. It's in the parentheses. It's input value. So f of x is really common to see, but sometimes we do like other letters. So I could say h is a function of x. And then I would call that h of x like that. Again, x is my domain. And then h of x is my range. So h of x is my range. So that's like my y value. And then x still is domain. F of x as well is like the range. So that's like our y value. I also don't have to use x. So I could say s is a function of t. This happens a lot. This is a position setup. So like a little physicsy. And so for this one, t is our domain, and s of t is our range, or kind of like our y value. And we'll come back to that. I do want to show you some more like, is it a function type? So example 2, determine if the following are functions. So A, we have y squared equals x. B, we have x minus 2 squared plus y plus 1 squared equals 9. And then C, we have 3x minus 4y equals 8. Now, I personally think that these will probably get easier for us as we go through chapter 2, because soon in chapter 2, we're going to start talking about how to graph. And I do think sometimes like looking at a graph and understanding what the graph would look like can really help with determining if it's a function or not. But the idea to think about is, if I pick one x value, is it possible for me to get two different y values out of that? So if I think about part A, or if you know what the graph looks like, you can kind of think of the vertical line test. But if I look at part A, let's say that I say y squared is equal to 1. Okay, I'm just going to pick an x value. Well, if I solve this for y, remember when you take square roots, it's plus or minus? So I'm getting y could be plus or minus 1. So what I've done here is I've picked one x value, and I've shown that I actually get multiple y values out of it. So no, this is not a function. Part B would be a similar process, but also we've done circles at this point. So this is a circle which does not pass the vertical line test. So no, not a function. And I like to show these because I feel like we kind of have this idea sometimes that, oh, if like anything is a function, or oh, if it's not a function, then we can't do anything with it. That's not true. It's just a different type of relation, right? Because a circle is still important to us. It's just not a function. For my last one, C over here, I could do either way. I could think about what the graph looks like, or I can think about if I plugged in an X, could I get a different Y? Now, I will say that we will do lines in our next section. Part C is a line. So this is going to be, yes, a function. It is just a line. And so again, I think that that'll become easier for us as we actually go through the chapter. Let's work with that function notation a little bit now. So example 3, I'll say let H be the set. So this one I'm going to come up with a set of points. And I'll say f of x, and I'll make something for this one, like a something more like what you'd be used to seeing for a function. And we're going to evaluate the following. So part A will say h of 7. B will do f of 7. C, I want w if hw is equal to 0. Then I have one more, but I'll run out of space, so I'll leave this. So remember, inside of the parentheses is your domain, or like your input value or your x value, whatever you want to call it for yourself. So with h of 7, we're saying that my x value is 7, and we're asking what is the y value that matches that. So if I go to my h function, my x of 7, my y value is 9. So h of 7 is equal to 9. Now let's do b together. So this is saying that my x equals 7. So what's my f of x, or my y value? So I'm going to plug this in to this function here. So I get f of 7 would equal square root, and I'm just replacing x with 7. So I get square root of 4, so that equals 2. For part C, I'm looking for w if h of w equals 0. So for this one, they're looking for the x, or the input, and my y value is equal to the 0. So if I look at h, my y value is 0, my x that matches that is 6. So we would say w equals 6 for this one, because that's what it was looking for, w. And I just let it be anything, like any kind of letter. I mean, I didn't have to use w. I could have used smiley face if I wanted. And then for part D, let's do one more. We'll say x if f of x is equal to 5. And again, I didn't have to write x for this. As long as you see that f function, you're dealing with the f function here. So this one is saying 5 equals square root x minus 3. So I'm looking for the value of x when the actual function itself, like my y, is equal to 5. So I have to solve this for x. So I'll square both sides. 25 equals x minus 3. Add 3 to both sides. I get x equals 28 for this one. So again, be careful about what you're being given. If you're being given the input or the output value. If you're being given the input, it's going to be in the parentheses, and you're looking for the output. If you're looking for, if they give you the output, so they'll write something like this, equal to something, that's giving you an output, and it's probably asking you for the input. So it might have to deal with some solving. Few more of these. So example 4, we're going to work a little bit more with some variables. So given f of x is equal to 3x squared plus 2x, I'll say find the following. Part A will find f of a. Part B will find f of x plus 2. And then for part C, we're going to do f of x plus h. So for all of these, I'm being given an input value and I'm being asked for the output. Now, none of these are like a pure number, so that means that at the end of this, we won't have a number, like we'll have more of like an expression. So if I'm looking for f of a, I'm being given f of x. So all I'm going to do is replace all of the x's with a's. So I'm just literally replacing what is in those parentheses. So now I'm going to have 3a squared plus 2a. And that's it. Part B, now I'm replacing the entirety of, instead of this x, so everywhere I see an x, I want to write x plus 2 instead. So for this one, I'll get 3, and we're going to have to utilize some parentheses here. So I have 3. Oh, right now I have an x. So instead of writing x, I'm going to write x plus 2. And then that's squared plus 2. Oh, and then I see an x. So instead of writing x, I'm writing x plus 2. So you're replacing the entirety of x with whatever is in those parentheses. And then we can simplify this. Be careful as you simplify. You have to do exponents first. So this is 3. And before we can distribute in the 3, we got to deal with the x plus 2 squared. Be careful though, x plus 2 squared is x plus 2 times x plus 2. So make sure that you don't distribute that squared. Keep going. I get x squared plus 4x plus 4. If I simplify that, I'll distribute this one, which gives me 2x plus 4. Now I'll distribute my 3. So I get 3x squared plus 12x plus 12. And then I have plus 2x plus 4. Combine like terms. I get 3x squared plus 14x plus 16. And that is fully simplified. Now for my part C, very, very similar. Everywhere I see an x, I'm going to replace it with x plus h. So I have 3, and then I have an x right here, so that's going to be x plus h, and it's still squared, plus 2, and then I have an x, so it's going to be x plus h. Just make sure you remember that if it's kind of if it's an expression that you're plugging in, you're going to want some parentheses. I'll expand this out quickly. So this is 3x plus h times x plus h plus 2x plus 2h. I did distribute that. Keep going. I get x squared plus 2xh plus h squared plus 2x plus 2h. Running out of space. There we go. 3x squared plus 6xh plus 3h squared plus 2x plus 2h. And combine like terms, 3x squared. Oh, I actually can't put anything together. Yeah, so that's the simplest. So I'm done right there. I was thinking there was something I could put together, but nope, there's nothing. So that's just some more stuff with that function notation. Next, we want to talk about x-intercepts and y-intercepts. Because they have a relationship with the function notation. So x-intercepts are real answers, meaning not complex. So we don't want any like i's or anything. Or I think in my notes I put solutions here, whatever you want to say, to f of x equals 0. And it's because graphically what happens here is when your y value is equal to 0, that means you're sitting on the x-axis. So you're going to intercept the x-axis in that place. So what's happening here is when my y equals 0 or my f of x equals 0, and then I would have to find the x that makes that happen. Now y-intercepts are real solutions to f of 0. So for this one, you're plugging in a 0 for your x. And what's going to happen there is that means that you're going to be on the x-axis whenever you're graphing. So for this one, we'll say when the x equals 0, we'll have to find the y value. And it's going to be on the y-axis. And again, this will just be important for us, especially as we start graphing soon. Let's do an example of finding some x and y intercepts. So example 5, I'll say find all x-intercepts and y-intercepts. And the function that we're going to be looking at is f of x equals x squared minus 4. So this is actually a quadratic. So for our y-intercept, we just plug in an x value of 0. So f of 0 equals, and so instead of writing x, I'm going to write 0. So I get 0 squared minus 4. So f of 0 is equal to 0 minus 4, which is negative 4. What this means is that on our graph, we're going to have a point, an xy point, that's going to be 0 for my x, negative 4 for my y. So this is going to allow us to start being able to plot points and stuff like that. Now let's look at my x-intercepts. And so now I need to let the f of x be 0. So I have 0 equals x squared minus 4. And there's multiple ways to solve this. You can factor it, or you can use square root property. I'm just going to factor since it's already on one side. So I get x plus 2, x minus 2. So x plus 2 equals 0, x minus 2 equals 0. I get x equals negative 2, and x equals positive 2. So this one I found 2 points. So I found the point negative 2 comma 0. So my x is negative 2, my y is 0. And I found the point 2 comma 0. So this is kind of where we're going soon. We're going to go into graphing and stuff like that and talking about how to find x-intercepts, y-intercepts for different functions. And relations too, really. Something that's kind of cool about quadratics is they're actually guaranteed to always have a y-intercept. They're not necessarily guaranteed to have x-intercepts because sometimes when you solve this kind of thing, like when you let your y equal 0, sometimes you'll get imaginary answers, so you'll get the complex solutions, and those result in you can't graph them, so there's no x-intercepts there. And I think I mentioned that a little bit whenever we did the quadratics unit. Now for our last example, I just want to talk about how to find domain and range. So we're going to do finding. Oh, I don't really like when it does that. There we go. Finding domain and range. Now I will say that range is a little easier to find whenever you know how to graph, in my opinion. But domain is, you kind of find it the same way each time. So let's see, this will be example 6. So I'll say for each of the following, we're going to find the domain and range. And we'll probably also talk about if it's a function. So I have a few of these to look at. I've got A. We're going to do one that's just a set of points. B, I have one that's a graph. I'm going to graph it with another color so you can see better. Let's see. Let's do some more of these. I'm just debating on whether I want to, write them down now or not. And I think I will. F of x equals square root x minus 3. And we'll do D. F of x equals square root 1 minus 2x plus 1. Alrighty. And you can always pause and write all these down, but I'll go ahead and get started. So for A, whenever it's written as a set, I actually kind of already talked about this. You just write down your domain is literally just your x points. So our only x values are negative 1 and 3. And then my range is just my y values. So I get 1, 9, negative 9. Now I don't really mind if you don't write them in order, but it is nice if we put them in order. And then let me also ask you, is this a function? Think of it yourself. No, it is not a function. And the reason is because I have the same x value going to different y values. So that is not a function. That's just a relation. Part B, we're looking at a parabola. Parabolas are quadratics. And so when we're looking at this, we're trying to see, so my x values will go all the way from negative infinity to infinity. So there are no x values that like I'm not going to touch at some point. So my domain here is negative infinity to infinity. Again, it'll probably help whenever you know how to graph more, because if you think about a quadratic, usually if there's a domain issue, it's because there is some kind of restriction with that function or relation, meaning, oh, if I plug in certain values, I'm going to get an error. And so with quadratics, there's no error that would ever happen. So you're free to plug in whatever x you want. Now my range for this one, I'm starting up here at +4, and it's going down to the bottom forever. So this is going to be negative infinity to 4. And that 4 would be in a bracket because it's included, because that point is included. Now, if I had put an open circle there, it would have been a parentheses, but it's a closed circle. So remember that from 1.7. Closed circle means bracket. Sometimes I'll have students ask me if they can write it like this. No, you always need to write the smaller part first. So negative infinity is smaller than 4. So we need to write it in order. Let's take a look at C. So C actually has a restriction. So square roots have restrictions. So I want you to think about what the restriction is for a square root. So with square roots, the problem is you never want the inside of a square root to be negative, because if that happens, then you have imaginary answers. So we want the inside of a square root to always be greater than or equal to 0. It can be 0 because we can take the square root of 0, that's fine. And then we always want it to be positive, so we never want it to be negative. So what I'm going to do here is I'm going to take this idea, inside the square root is x minus 3, and I'm going to set that greater than or equal to 0. For my domain. Because what I'm saying is, what are the x values that I'm allowed to plug in here that are not going to give me any kind of error? So if I finish solving this, I would add 3 to both sides, and this gives me x has to be greater than or equal to 3. Now we also like to write this in interval notation. So my domain here, if x has to be greater than or equal to 3, I'm saying it can be 3 to infinity. And the 3 is included because it's a greater than or equal to symbol. And the infinity gets a parentheses because we can't actually plug in infinity. But again, what this is trying to tell us is, okay, I can plug into the x value anything bigger than 3. So I can plug in 3, and I can plug in anything bigger than 3. If I plug in anything outside of this domain, I'm going to get an imaginary answer. So I'm going to get an error. Now again, I can't say this enough to you. Range is a lot easier if you know what the graph looks like. But I'll show you. If we plug in our lowest value, so the lowest value we can possibly plug in, so I'm trying to find the range right now. The lowest value I can possibly plug in is 3. If I plug in 3, I'm going to get 0. So let's see what happens if I plug in bigger than 3. So I'm kind of working through my domain a little bit, like seeing what happens if I plug in bigger. Okay, if I plug in bigger, it goes up a little bit. It goes up to 1. What if I plug in, let's think of something. What if I plug in 7? So I get square root of 4, so that's 2. Okay, good. So what's happening to my y values is they're getting bigger and bigger as I plug in bigger and bigger x's. So my range for this started at 0, that's the absolute lowest I could get, and it'll just keep going up to infinity. So my domain is 3 to infinity, and my range is 0 to infinity. And I'll do a very similar idea for part D. So for part D, again, I'm seeing a square root. So the restriction for square roots is we want the inside of the root to always be greater than or equal to 0. So 1 minus 2x greater than or equal to 0. And this is finding my domain. Let me write that for us. So we're finding domain right now. And so I'm going to solve this inequality. So I'll subtract, let's add the 2x to both sides. That way we can just make that positive. So I get 1 greater than or equal to 2x. I would divide by 2, and I get 1/2 greater than or equal to x. If I read this from the x point of view, I guess you could say, it's saying x has to be less than or equal to 1/2. So my domain for this one, x has to be less than 1/2. So that's going to be negative infinity to 1/2. Now for my range, this one's kind of interesting because we're going like the opposite way. So I still want to plug in for this one, my biggest value I can plug in is 1/2. So let's see what happens when I plug in 1/2. I get square root 1 minus 2 times 1/2. I run out of space. And then I'll have to add 1. You'll notice that that plus 1 did not matter at all for the domain. It didn't matter to us. It doesn't matter if there had been a number out here either. Wouldn't have done a thing. All we cared about for domain is in the root. All right, so I'm going to solve this, see what I get. So I'll get square root. This will be 1 minus 1 plus 1. So I'm going to get 0 plus 1. So I get 1. So that means that for my range, my biggest value that I can get is 1. Or is it my smallest? We'll have to see. But I know that that 1 is going to either be on the left or the right. Let's see if I plug in something else. So you can ask yourself, do I want to plug in numbers that are smaller than 1/2 or bigger than 1/2? If you plug in stuff that's bigger than 1/2, you're going to start getting imaginary solutions, so it's not going to be helpful. You want to make sure you stick to your domain. So I'm supposed to plug in stuff less than 1/2. So let's just see if we plug in, let's just say 0. So I get square root 1 minus 2 times 0. Then I'll add 1. So this gives me 1 plus 1. So that's going to give me 2. Okay, so it's looking like I'm getting bigger. If you need to see another one, plug in another one. Let's do -1. So I get 1 minus 2 times -1 plus 1. So this will give me 1 plus 2 plus 1. So I get square root of 3 plus 1. That is going to be bigger than 2. So for my range, I'm seeing that my smallest number was 1, and then I just keep getting bigger and bigger. So this is 1 to infinity for the range. Something kind of interesting is actually this 1 right here is because of this 1 right here. And we'll learn that when we do transformations, when we learn how to graph. But what's happening is whatever you get underneath that root, you're always adding 1 to it. So of course you're going to get bigger stuff than 1. You're having, like, the lowest value you can get is adding 1, and then you're just going to keep adding on to that. So it's just going to get bigger. Now I actually have 2 more for us for this section. So part E, this one says g of a. Oh, for these I'm going to make a point. Only find domain for G, sorry, for part E and part F. The reason is the range is just a bit difficult, and we actually don't learn how to graph these in this class. If you go further, you'll learn how to graph them, but we actually won't graph these in here. But it's still good to know the domain and stuff. All right, so again, you can pause and write it down and stuff, but I'm going to go ahead and get started. So with part E, you want to always think, when you're thinking domain, you want to think, are there any restrictions? Like, are there any problem areas with this function or relation, whatever we're dealing with? The issue with this is that denominators cannot equal 0. We never want a denominator to equal 0. So when we find our domain, we're going to take what I call the problem area, which in this case is our denominator, and we're going to set it not equal to 0. So before, right, for the last 2 we did, the problem area was underneath the root. So I took the root, and it just needed to be greater than or equal to 0. For this one, my problem area is my denominator, and I just don't want it to be 0. And so we've actually talked about this kind of idea before, but I'm not sure that I really said that it was finding domain. I think we probably just said, like, finding restrictions, but it's just that x can't be 2. And so when you write this in interval notation, this will be negative infinity to 2, union 2 to infinity. You're saying everything before 2 is fine, everything after 2 is fine. You just can't plug in the number 2. And that's it. Now for part F, This one, it kind of puts it together. So we have to think about multiple restrictions happening. So one, denominators can't be 0. So I'm going to write that here. So denominators can't be 0. And then also we have a root. So inside of a square root has to be greater than or equal to 0. So what we're going to do is we're basically going to combine these concepts. So my problem area here is the 2x plus 1. And usually inside of a root, I would just say, oh, greater than or equal to 0. However, because I'm saying that it can't be equal to 0, I'll just get rid of the equal to bar. So I'm saying that actually for this one, I need the inside of the root to always be greater than or equal to 0. But then also because it's in the denominator, I actually don't want it to be 0. So I'll just say greater than 0. And then we solve. So 2x has to be greater than -1. Divide by 2. I get x has to be greater than -1/2. In an interval notation, so parentheses, because no equal to bar, -1/2 to infinity. So for this one, we just kind of had to put them together. And yeah, graphing something like this is a bit more difficult. Here at Tech, we really only learn how to graph stuff like that starting in Math 241, which is our Calc 1. So we'll find the domain of it. We'll find that there are certain x values we don't want to plug in or we do want to plug in, but we won't worry about the actual graph. So I wouldn't ask you for the range for this because it's a bit complicated. So I hope this is all right. If you ever have any questions, of course, as always, email me. But this is this is going to be it for this section. The next section is lines. So we're going to move on to lines soon, which is exciting. So I hope y'all have a wonderful day, and I'll see you next time. Bye-bye.